Yeah, hi, Professor Burtsakas, can you hear me? Am I audible? Can you hear me, Professor Burtsakas? Can you hear me, Professor Burtsakas?
Yes, I can hear you.
Okay, thanks. We'll get started. I'll first introduce you briefly and then we'll get started with your talk. Is that fine?
Okay, you give me the signal.
Okay, thanks a lot. So it's an honor to have Professor Dmitry Burtsakas from the Arizona State University. He taught for a very long time, almost 40 years at MIT, and he is extremely well accomplished. Has received lots of awards and honors over a career spanning several decades, and he has written several important textbooks that are widely followed worldwide. Textbooks on dynamic programming, optimal control, optimization, convex optimization, nonlinear optimization, and so forth. We in fact follow a lot of his course material in the courses that we teach. More recently, he has been actively writing a lot of books on reinforcement learning. It's really an honor to have Professor Burtsakas with us. You can see the audience, I guess, and there are also people sitting on the left flank and the right flank, which probably you won't be able to see, but I guess you'll have an idea of how many people are there, and so on. People are still coming in, but I guess we'll get started with your talk. So let me welcome Professor Burtsakas let's welcome him with a wide applause. Over to you, Professor Burtsakas. It's all yours.
Okay, thank you very much, Shalab. It's my pleasure to give this lecture on computer chess and its relations to model predictive control and reinforcement learning. This is material that's based on my course at ASU, and particularly the last two books that I've written. One is already available on the internet and is about to be published in print. This lecture is also connected with a computer chess paper that I have written with two colleagues, Yuchao Li and Atharva Gundawar, and you can find it online. So let me give you the outline of what I'm going to talk. I'm going to discuss the relation between reinforcement learning and model predictive control, MPC. And I'm going to use computer chess as a vehicle for that. Then I'm going to discuss a theoretical framework for MPC that's based on Newton's method for solving the Bellman equation. I'm going to discuss first one-step look ahead and then MPC with multi-step look ahead. And then I'm going to come back to computer chess and how we can improve the performance of any given chess engine using model predictive control. So let me first talk about a remarkable computer chess program, AlphaZero, which came out a few years ago and created a great deal of enthusiasm for the prospects of reinforcement learning. Now, AlphaZero and most chess programs involve two algorithms. The first is the offline training algorithm, which trains a position evaluator using machine learning and deep neural networks in the case of AlphaZero. And this is the algorithm that whereby the program learns how to evaluate positions and how to play based on these evaluations. And then there is the online play algorithm that it used to play online with human and computer opponents. And this involves multi-step look ahead with a position evaluation at the end. Now, most attention has been focused on the offline training algorithm of AlphaZero, which involves some important innovations in deep neural network technology and other things. Now, the online play algorithm is more or less traditional, has a lot of commonalities with the algorithms that have been developed, the programs that have been developed in the past, and it's the one that's critically important for good performance. And also the online play algorithm in computer chess generally is strongly connected with MPC. So let me first discuss the MPC in a form that's convenient for the purpose of this talk. It's applied to discrete time deterministic optimal control. It involves a deterministic system where xk is the state at time k, uk is the control at time k, and the state evolves according to this equation. And there's a cost per stage, which depends on state and control. And MPC involves multi-step look-ahead optimization with cost approximation, a function j tilde at the end of the look-ahead. And in particular, at a given state xk during online evolution of the system, we solve an L-step look-ahead problem with a terminal cost function j tilde. The problem that we solve is the following. The cost function is the sum of the cost of the first L steps following stage k, plus a cost function approximation, which approximates the future stages and depends on the stage at the end of the look-ahead. So this is an L-step deterministic optimal control problem, which can be solved to give a sequence, an optimal sequence. We apply the first control in the sequence, u tilde k at xk, and we discard the remaining controls. And then we apply this control at xk, and then we go to the next state, xk plus 1, and do the same thing, and so on. So that is MPC. And now let me talk about computer chess in the online play algorithm computer chess. The chess position is the state in this particular case. It evolves over time. At the kth stage, we have a position. And here we consider all possible legal moves. This is the control that we apply. The opponent also chooses a counter move. And this is continued for several moves. And then at the end of the look ahead, we evaluate the position, back up the computations to the current position, and find the best move. So again, it is multi-step look ahead with a position evaluation at the end, like MPC. It's basically, this architecture is basically isomorphic to the MPC architecture, except that in chess, the state and control spaces are discrete, while in MPC, they are usually continuous. Also, in chess, the look-ahead tree is usually pruned. We don't consider all legal moves, but instead only the ones that seem most promising according to some criterion. On the other hand, in MPC, the look-ahead optimization is usually exact. And we're going to discuss this a little later, and this is going to be significant in what I'm going to talk about later. Now, these two differences, I will argue, are inconsequential, and our Newton step theory allows arbitrary state and control spaces as well as inexact look-ahead. There's also another difference. Chess is a two-player game, while MPC involves one-player optimization. You can think, however, chess as a one-player game if you view it as chess against a fixed opponent. So we get to know the moves or predict the moves of the opponent, and then it becomes a one-player game. Now let me give a summary of the principal viewpoints of this talk. I'm going to argue that one online play with one-step look-ahead is a single step of Newton's method for solving the problem's Bellman equation. And there's a similar interpretation that applies to multi-step look-ahead. And the offline training algorithm provides the starting point for the Newton step. The online play algorithm, however, is the real workhorse, and by comparison, the offline training plays a secondary role. Then I'm going to argue that the Newton step framework is very general because it's couched on abstract dynamic programming ideas, which allow arbitrary state and control spaces, stochastic problems, deterministic problems, hybrid systems, multi-agent systems, minimax, anything goes. This Newton step framework applies very generally. And then the other point that I want to make is that by using an architecture whereby we integrate existing chess engines, we can obtain favorable results. In particular, we can beat the engines on which are involved in our architecture. So the Newton theoretical framework for MPC, I'm going to explain this in terms of a visualization for linear quadratic problems. And I'm going to consider this is a very, very well-known framework, a linear system and a scalar system for the purpose of visualization. A and B are given scalars. The cost function is quadratic. Q and R are given positive scalars. And there are very well-known facts about this. The optimal cost function is a quadratic function of the state, and the optimal control policy is a linear function of x. And in particular, the optimal cost function is this quadratic, where k star is a scalar that's obtained as the unique positive solution of the Riccati equation, which is a fixed point equation with this Riccati operator given by this equation here. And the optimal policy is linear of this form, where L star is a scalar that's calculated in terms of k star by this formula. All of this is very well known. I'm giving it for one-dimensional problems. There are generalizations for multidimensional linear quadratic problems. And moreover, the insights that I'm going to give you based on this simple problem generalize very, very broadly. So let me illustrate graphically the solution of the Riccati equation. Here is k, the cost coefficient, and the red curve is the graph of the Riccati operator given here. To obtain the solution of the Riccati equation, we have to find a fixed point of this operator. So we intersect this red graph with a 45-degree line. We obtain this point here, and this is k star, the optimal cost coefficient. Let me also illustrate the value iteration algorithm, which generates iteratively the cost functions of k-stage problems. This is the cost function of the infinite horizon problem. The value iteration generates the optimal cost function of k-stage problems, iterates with the Riccati operator up until convergence to k star. Now, these k-stage problems have cost functions that are quadratic with a coefficient k of k, which is obtained by iterating like so, starting from a given initial condition. And graphically, at the typical iteration, we have kk. To obtain kk plus 1, we go up here. And then we reflect along the 45-degree line, and this is kk plus 1. Then kk plus 2, and then kk plus 3, and so on. So the iteration is represented by this staircase evolution towards k star, and it converges to k star. Now, let's also look at the Riccati equation for linear policies. Let's consider a linear policy of this form. L is some scalar, and let's consider its cost function. It is quadratic of this form. KL is the unique solution of a corresponding Riccati equation for linear policies. It's also a fixed point equation with an operator f of L, which, however, is linear. It's linear in k. This is the coefficient of the linear term, and this is the constant. And the policy is stable if this linear coefficient is less than 1, and it has a linear graph like so. It slopes at an angle less than 45 degrees. But there are also unstable policies which have graphs that slope at an angle greater than 45 degrees. And so this is the Riccati equations visualization for linear policies. And now let's visualize MPC with one-step look ahead. So we have this red graph here, which is the graph of the Riccati operator. And we have these graphs of the policies, which are lines. And all of these lines lie above the red curve, clearly, because these are suboptimal policies. And you can show rather easily that the graph of the red curve is the lower envelope of this lines. So we have all these lines, and some of them go down and touch this graph of the Riccati operator. If you take the lower envelope, you obtain the red curve. Now, let's consider MPC with a terminal cost function approximation that's quadratic with coefficient k tilde. How can we visualize that? Well, we go up here and we take the tangent line. This is the MPC policy for one step look ahead corresponding to k tilde. And the cost function of this policy is obtained by intersection with this 45-degree line. It's over here. So what we do to visualize MPC, we linearize the Riccati operator at k tilde. And then if we look at this graph here, we see that it's exactly Newton's method. In order to find the fixed point of a nonlinear equation, Newton's method, at the current iterate, you linearize the operator, solve the linearized problem, and then that's your next iterate. So MPC does one step of Newton's method starting from the cost function approximation coefficient. Let me also note that the concavity of the Riccati operator is also important for this figure to be valid, and it's important also for the more general theory that generalizes this figure. So here's another view of the Newton step. Riccati operator, cost function approximation, the MPC policy, and we obtain here the cost coefficient of that policy. And the Newton step takes k tilde into this KL. And the convergence, of course, of Newton's method is superlinear as long as you are within the region of convergence, which means that this error is tiny relative to this initial error. And that explains the good performance of MPC in practice. If you are within the region of convergence of Newton's method, MPC works very, very well. Excuse me. So let's now look at the corresponding picture for multi-step look ahead. To understand multi-step look ahead, it's important to realize that it's really one step look ahead with a different starting point. A starting point that's obtained by applying L-1 value iterations to k tilde, or the cost function approximation corresponding to k tilde. So there's an initial step of the look ahead, and then the remaining L-1 steps, and then the quadratic cost approximation. But only the first step is the Newton step. The remainder just serves to bring k tilde closer to the optimal solution by means of value iterations. So in terms of a different kind of visualization of the Newton step, we have cost function approximation k tilde for two-step look ahead. We first apply a value iteration, and then we apply the Newton step. And that's what we obtain from two-step look ahead MPC. That's the two-step look ahead MPC policy. If we had 10-step look ahead, then from k tilde we take 9 steps, and then finally the 10th step would be the Newton step. So this highlights the importance of the first step of the look ahead. It's only this first step that's the Newton step. The remainder serves to bring the starting point close to the k star. So this can be done approximately, but this has to be done exactly in order to be an exact Newton step. So that's an important insight. The first minimization step should be done exactly, while the remaining steps can be done approximately. And this has far-reaching practical implications. I'll give you one example. In stochastic problems, for which this Newton step interpretation also holds, we can use certainty equivalence approximations for all the lookahead steps except the first one. And this simplifies the computations tremendously, and also with relatively little degradation in performance. And this fact has been verified with computations over a long period of time, starting with my work with David Castagnon more than 25 years ago. And there are other contexts also where approximations in the subsequent steps of lookahead can be of important significance. So now let me go to computer chess using MPC. At ASU, we have done quite a bit of work involving discrete state and control spaces, combinatorial problems. I'm listing some of those here in collaboration also with Stephanie Gill. I'm excited about this work, which is very recent. It has to do with a Viterbi rollout algorithm, an algorithm that is a simpler version and far more computationally efficient than the Viterbi algorithm, and therefore applies to large-scale problems. But for now, I'm going to focus on computer chess. And we have an architecture in which we introduce existing chess engines for the purpose of playing better computer chess. So we introduce a one-player MPC architecture where the true opponent is approximated by a nominal opponent. In particular, this architecture involves two chess engines which are available. And these chess engines are components. So this is a meta algorithm that incorporates other algorithms into an architecture. The first engine is the nominal opponent engine. It's used to predict the move of the true opponent of that we're playing against. So instead of having a minimax player after we play our move, we substitute that with the play of a known engine. Then we have a second engine that evaluates the position at the end. And in this way, we have a Newton step starting at the position evaluation. And the calculations involved here are looking at all possible legal moves, then generate the predicted value of the opponent, and then evaluating the result and choosing the best move. So that's our architecture, and the important thing to note is that these evaluations can be done in parallel, and these evaluations can be done in parallel. So that's important for the computational efficiency of the algorithm. And now let me give you some computational results that we have gotten using as nominal opponent and position evaluator the Stockfish engine. Stockfish is a well-known chess program, a champion program. It's been around for many years. It's used as a benchmark for evaluating other chess engines. And in these results, we have, that I'm going to show you, we have tested two variants of the algorithm, the standard version and another version, which we call fortified. And let me not explain what this is. It's a little more conservative, plays a little better against very strong opponents and a little worse against weaker opponents. And here are the results of some chess matches. We have our architecture, MPC-MC, that uses Stockfish engines as components, and we play them against Stockfish. And each one of these entries represents a 10-game match. We have tested against 3 Stockfish engines of different strength at half a second per move. This is a pretty good chess player. At 2 seconds per move, it's a very strong chess player. And at 5 seconds per move, Stockfish is almost unbeatable. It plays almost perfect chess. Now, the numbers here represent the score as customarily recorded in chess. 1 point per win, half a point per draw, 0 point for loss. So this means, okay, MPC-MC has lost in all these matches, did not lose a single game. And in this particular match, it won 5 games and drew 5 games. In this match, won 6 games and drew 4 games, and so on. This involves a nominal opponent, which is exactly known. This involves a nominal opponent for which some noise has been introduced. And you can see that for this weaker strength Stockfish engines, we decisively win. And as Stockfish becomes stronger, we have more difficulty getting an edge, but still we do get an edge. Of course, at 5 seconds, Stockfish plays almost perfect. It's very hard to beat. We have also done a lot of tests with using weaker engines, Komodo Dragon, other engines, and we have obtained better results, actually. And we can also show better results with multi-step lookahead, although we have not done extensive tests in this regard. And as I mentioned earlier, parallel computation is essential in order to reduce the move generation time. So this gives you an indication of our results. To us, they were quite surprising, and it's worth asking why this is so. What's the reason? Now here, I can't offer you any assessment with certainty. It's only a speculation. Our consistent observation is that MPC-MC improves the play of weak base engines decisively and the play of strong world champion level base engines narrowly. And so why is this happening? After all, MPC-MC looks ahead 1 more step. Chess engines look forward 20 steps, 30 steps. So we add only 1 more step of look ahead, and yet we're getting such an advantage. So we looked a little bit more into this, and one observation here is that MPC-MC plays mostly the same moves as the base engine. So it replicates the moves of Stockfish, the engine that does the evaluations, plays the role of nominal opponent, but occasionally it varies in like 10–20% of the moves. Like once in every 10 moves, you get a different move by MPC-MC, but oftentimes this is important. Sometimes the base engine misses some hard-to-find strong moves at the very first of look ahead. It prunes it out, thinking that they are not promising. On the other hand, MPC-MC does not prune out anything. It has to do with the first step of look ahead has to be exact. No approximations in order to be able to replicate the Newton step. So that's where I think that MPC-MC gets an advantage, and because it performs a true Newton step. Now, all of this is quite counterintuitive. Why the first step and not the subsequent steps? However, it's consistent with a lot of experience, it's consistent with theoretical insights, and with much experimentation with other reinforcement learning and MPC case studies beyond chess. So that's my final slide, and thank you very much for your attendance.
Right, thank you, Professor Bartsakas. We have time for some questions.
Yes, if you could speak a little bit more loudly.
Yeah, one second.
So, Professor Bartsakas, I hope you can hear me. Can you hear me?
If you could speak a little more loudly.
Professor Bartsakas, can you hear me now?
I can hear you, yes.
So my
Speak
question,
slowly and loudly if you can.
Yes. So you spoke about this multi-step look ahead. I wanted to understand in this game of chess, how challenging does the multi-step look ahead become as you start looking more steps ahead, and how do you deal with the challenges that result in this multi-step look ahead?
Well, our architecture and the results that I've presented use one-step look-ahead. With multi-step look-ahead, like two-step, for example, there's another layer. And it increases the computation, of course, but we haven't tested anything beyond 2 steps. And the generalization to multi-step look-ahead is straightforward. It's just that the computation increases. If you look at my paper, you'll see diagrams that explain the multi-step look-ahead.
And maybe a follow-up question. So in your calculations, do you work with function approximation, or in some sense you work with perhaps the tabular setting?
The cost function approximation at the end is provided by the Stockfish evaluation. I'm not sure I understand your question.
Okay, maybe I'll look at your paper and then maybe get back to you. Thank you.
You also mentioned about the stochastic version of the problem. So do you look at maybe the RL version as well, or which means you just have access to data, you don't really have access to the model information?
I spoke about an approximate opponent, a stochastic opponent. Is that what you mean in the computer chess, or generally in MPC?
In generally, because you said the first step has to be exact, the Newton step.
Yes.
So the thing is, if you just have access to noisy data, I mean, how exact can you be?
Yeah, the first step is going to be stochastic. So if you have, so you have to take into account the disturbance, the stochastic disturbance in the system equation, in order to generate the set of all possible next states. In other words, from xk, you use the stochastic equation to obtain all the possible xk plus 1. And then when you do the subsequent approximation for subsequent steps after the first one, then you can use certainty equivalence. You can use a deterministic system to make your predictions forward.
Sure.
So that's where the savings come. If you have like 10 steps of look ahead, then the first step is stochastic. The other 9 steps are deterministic. So the look ahead tree is much, much smaller.
Sure. Okay. Thank you. Yeah. Any other questions? Yeah, one second.
Hi, Professor Bertsikas. When you presented the empirical results, you're playing against the Stockfish base model, let's say. And is your position evaluator also the Stockfish base model?
In the results that I have presented, we play against Stockfish, and the 2 engines are also Stockfish. The position evaluator engine is Stockfish, and the nominal opponent is Stockfish as well. On the other hand, this is not necessary. We can play against Stockfish, the real opponent, and we can use a different nominal opponent, like Komodo Dragon, some other chess engine. And we can use a position evaluator that's still a third engine, a different engine. So in an actual match, there can be as many as 3 engines: the real opponent, the nominal opponent, and the position evaluator. And of course, the results depend on what engines you use and who you play. That predicts the value of the opponent is a fairly good engine. You cannot have a weak opponent and then make predictions, because these predictions are unreliable.
Thank you. Another follow-up question. This method is not particular to chess. So if you apply this to Go, you'll get similar results, I would think.
Absolutely. It applies to any 2-person game, deterministic, however. It does not apply to things like poker or backgammon. It applies to Go. It applies to a Chinese version of chess. Any two-person antagonistic board game.
Thank you.
And we actually are trying to apply this methodology more broadly, but there are so many games, it's going to take us a long time before we exhaust them.
All right, so let's thank Professor Bertsikas. Thank you very much, Professor Bertsikas, for your excellent talk.
My pleasure. Thank you.
All right, so we'll have